Okay, so hello everyone. Thank you for joining this seminar today. And we are pleased to host today Dr. Meng, who is Associate Professor at the Institute of Interdisciplinary Research for Mathematics and Applied Science in China. He also received his PhD at the same university in 2017, and he was a postdoc at Brown University after his PhD, supervised by Professor Kaniadakis. His research, so Dr. Meng's research interest is specific in scientific machine learning, which is the topic of today's talk. In particular, his interest is focused on developing certainty quantification methods for scientific machine learning algorithms. You can find some very useful, I think, packages for this research on Dr. Meng's personal webpage as well as on GitHub. So I do suggest referring to the advertisement of this talk for the specific links. I just like to remind everyone that the talk is being recorded. If you like to ask questions, we have some question time at the end of the talk, so you can either write your question in chat or just turn off your microphone and ask a question. So without any further ado, Dr. Meng, the floor is yours.
Okay, thanks for the introduction. Today I will be talking about deep learning for solving forward and inverse PDE problems. It's about some models we developed and also applications of our models. So in the first part of my talk, I'll talk about universal approximation theorem of deep neural networks. And then I will introduce how to encode PDE in DNNs to get physics informed neural networks, which we call PINs. And then I will introduce three deep learning models we developed. The first one is PIN with multifidelity data. We call it multifidelity PIN or MPINs. And also two uncertainty quantification methods to quantify uncertainty in in PINs and also neural operators. And with the summary. So this is a schematic of deep neural networks. It has multiple layers, an input layer, one or more hidden layers, and output layer. And in each layer we have a certain number of neurons. We also have a collection of one collection between each two neurons. Represents the weight and biases, and the output of each layer is a linear compilation of its input and also the weights and biases plus the nonlinear activation, nonlinear transformation. These are two widely used nonlinear activation functions, sigmoid and tangent H. And in this paper, the authors prove that this neural DNNs with this kind of architecture are capable of approximating any measurable functions to any designed degree of accuracy. And the convergence rate also changes with the number of the neurons in hidden layers. So in practice, if we would like to fit a function using a deep neural network, we can try to optimize the volume loss function, which is the mean squared error between the output of the neural network and the given data. We can use the stochastic gradient descent to get optimal weights and biases of the neural network to make our neural network, the output of the neural network, to match the given data, which is why I start here. And here is an example of function approximation case. The target function is a discontinuous function. On the left part, we have a low frequency function, and on the right part, we have a high frequency function, and in the middle, we have a discontinuity. And the red dots are the predictions from a neural network at different training steps. And the black solid line is the reference solution, as we can see. And let me play it again. So now the neural network first fit the low frequency part on the left, and then the high frequency part on the right. And this is the prediction of a neural network at different training steps in the frequency domain. And this is the prediction at the physical domain. We can also say that the learning mode of a neural network is from a low frequency to a high frequency. And this is the basics of all our method, all our proposed, all our deep learning models. And here is the schematic of pins. So we have a neural network to serve as a circuit to the solution of a PDE. And based on the automatic differentiation, we can express that we can express the derivatives using automatic differentiation based on the chain rule. And if we would like to solve a differential equation, we have the boundary condition and no initial condition. We can use a loss function. We can use a loss function here. The first term is the residual between of a differential equation, and the second term is the mismatch between the prediction of a neural network and the given and the measurements for the boundary condition. And the last term is the prediction of a neural network of a neural network. It's the mismatch between the prediction of neural network and the given measurements on the initial condition. By minimizing the following loss function, we can by minimizing the loss function, we can try to solve the differential equation. After training of a neural network, the output of a neural network will satisfy the boundary condition and also initial condition as well as the equation itself. And we can also use the same framework to solve an inverse problem. By inverse problem, I mean we have some measurements on the solution of the equation, and we also have some unknown constant or unknown field or unknown functions in the equation. So we can use the following loss function to solve the inverse problem using pins. The first term is the same as in the loss function, which is the residual of the equation. And if we have measurements on the boundary condition or initial condition, we can also use them in the loss function. And the star is the measurements, is the partial measurements, partial observations on the solution to the PDE. And the U is the output of the neural network. After training of the neural network, we can get an estimate of the solution to the PDE. We can also get a predict. We can also infer the unknown constant or unknown fields or unknown functions in the PDE itself. So as you can see, PIN is a unified framework for solving forward and inverse PDE problems. And since we use automatic differentiation to approximate the derivative in the equation, we don't need to generate any discrete meshes, which is different from the numerical solvers. Now we'll go to the multifidelity PIN with the multifidelity data, multifidelity PINs. So what is the first question is what is multifidelity modeling? Say if we would like to fit this function, the black solid line here, but we only have 4 high fidelity measurements for this function. If we just use these 4 measurements to fit this function, it's very difficult to resolve the details because we don't have enough information. And also we also assume that we have another type of measurements, which are the blue points here. That there are also measurements for this function YH here, but they're not so accurate. So but they're not so accurate, but they are very cheap. So we can have lots of them. So it's very easy to fit this function, which is represented by YL here. And if we have UYH, the black solid line, as a function of the low fidelity function here, the correlation between the low fidelity function and the high fidelity function is very easy. So we can just use a very few high fidelity data to learn the correlation between low fidelity and high fidelity function. So we have lots of low fidelity measurements, so we can determine, we can learn, we can fit the YL easily. Once we use the high fidelity data to determine the correlation between low fidelity and high fidelity function, we can then get the prediction at any location for the high fidelity function, right here. And multi-fidelity modeling, the applications of multi-fidelity modeling has been found in different engineering applications, from aircraft design to a sea surface temperature forecast. For example, in the second example, we would like to predict, let's say, the sea surface temperature in this area, and we have two types of data. The first type is from the satellite. The satellite data can cover the whole area, but the resolution is very low. So we can use it as a low fidelity data. And we also have another type of data, which is from the institute measurements or from stations. These measurements are very accurate, but we don't have lots of them. So the objective here is to simulate both the low fidelity data from satellite and high fidelity data from institute stations to enhance the predicted accuracy for the sea surface temperature. I have a detailed example in flows. I'll show the details to you later. So in the multi-fidelity modeling, we have two types of data: low fidelity data and high fidelity data. The low fidelity data are not so accurate, but they're very cheap, so we can have lots of them. Generally, we can use the numerical simulation or empirical models to generate low fidelity data. For the high fidelity data, they're very accurate, but they're quite expensive, so we can only have a very small number of them. And the high fidelity data can be from experiment or field observations. So in the multi-fidelity modeling, the low fidelity data is used to supply the trend towards the high fidelity data, and the high fidelity data is used to determine the correlation between the low fidelity and high fidelity data. The key of the multi-fidelity modeling is to learn the correlation between the low fidelity and high fidelity data. This is the most popular multi-fidelity model. It's the multi-fidelity. It's based on the Gaussian process regression. So in this method, we first use a Gaussian process regression. We first use a Gaussian process to fit the low fidelity data, and then we assume that a low fidelity correlation between the low fidelity and high fidelity data is linear. Rho is unknown constant, which will be determined by the data, and data here is a bias, which is also approximated by a Gaussian process. So data is a Gaussian process, and YL is also a Gaussian process. The linear combination of these two Gaussian processes is also a Gaussian process. And then we can use the optimizer to learn the optimal hyperparameters such as rho and the hyperparameters in institute GPs to get the optimal parameters in these models. And recently, this method has also been extended to PDE programs, but they can only be used to solve linear PDE programs. So in the multi-fidelity GP, since we have linear assumption here, they can only be used to handle the programs with linear correlation between low fidelity and high fidelity data. And if we use this method to solve PDE programs, they can only be used to solve linear PDE programs. And GP cannot handle big data. And to address these three issues, we propose the new framework based on the deep neural networks, which is multi-fidelity deep neural networks. And if we use the idea of pins to solve inverse PDE programs, it's a multi-fidelity pins. So this is a schematic of the proposed method. We first use a neural network to fit low fidelity function. And if we use the low-fidelity high-fidelity function as a function, high-fidelity data as a function of the low-fidelity data, we can then use a nonlinear network to learn the correlation between the low-fidelity and high-fidelity data, which is represented by capital F here. And if we have the information of PDE, we can also use the automatic differentiation, just like in pins, to encode the PDEs in the neural networks. So the loss function for training these neural networks is the mean square error for the low fidelity function, the mean square error for the high fidelity function, and the residual of the PDE. So in the first test case, we'll try to generate low fidelity data and high fidelity data from these two functions. And the correlation between the low fidelity and high fidelity data is linear in this case. In this case, we assume that we have only 4 high fidelity data, which are the red points here. And if we only use the high fidelity data to fit this function, I use 2 methods, neural network and also creating is also is also a DP to fill these 4 data, and these are the prediction we get from those 2 models. They are also accurate. And if we assume that we have some low fidelity data here, and we can use our proposed method to estimate the low fidelity data and high fidelity data. And this is a prediction from the multi-fidelity modeling. The black solid line here, which agrees well with a reference solution. And as I mentioned before, the key in the multi-fidelity modeling is to learn the correlation between the low fidelity and high fidelity function. Here I also plot a predicted correlation from the neural network and the reference for the correlation. So as we can see, the predicted correlation agrees well with a reference correlation. Now, because we use the neural network to learn the correlation between low fidelity and high fidelity data in our multi-fidelity DNNs. And as I mentioned before, DNN is capable of learning both linear and nonlinear functions. So our method is expected to handle the nonlinear correlation between low fidelity and high fidelity function data. So in the second case, we generate low fidelity data and high fidelity data from these 2 functions. And now, for this case, the correlation between low fidelity and high fidelity data is nonlinear. And we assume that we have 14 high fidelity measurements in this case. If we only use high fidelity data, that's what we can get. That's what we get. That's what we can get from neural network. The red dashed line is the prediction from single fidelity neural network. And if we assume that we have some low fidelity data from this function, and try to use the multi-fidelity approach proposed to assimilate low fidelity data and high fidelity data here. And the red dashed line is the prediction from the multi-fidelity DNN, which agrees well with the reference solution. And this is the prediction for the correlation, which also agrees well with the reference solution. And we also use this method to test the function approximation case in 20 dimensions. And we use these 2 functions to generate low fidelity and high fidelity data. So in the first case, we just randomly stacked 5,000 high fidelity location. We just stacked 5,000 locations and then get the function value from this function and use them as the training data to see if we can use a neural network to fit this function. And this is after the training of the neural network, we can get a prediction at 10,000 random locations. And as we can see in the predictions are also accurate. And then we assume that we have 30,000 low fidelity data here. and try to use our method to assimilate the low fidelity data and high fidelity data to perform the multi-fidelity modeling. And as we can see, the results are much better than a single fidelity modeling. So in addition to the function approximation case, we can achieve very high accuracy based on a very small number of high fidelity data. So in pins, if we would like to solve an inverse problem, we also need to have some. We also have to require some measurements for the solution. So to reduce the number of the high fidelity data in solving inverse PDE problems, we can also use our proposed method to assimilate low fidelity data and high fidelity data to achieve high accuracy in solving inverse PDE problems. For example, here is this is a W equation for one-dimensional unsaturated flows, and H is the pressure and K is the permeability field. And this is a commonly used model for the permeability field. In this model, we have two parameters, alpha and M, which are related to the pore structures. For example, for different soils, we have different values, which are these two values are very difficult to measure directly. So in this case, we try to infer alpha and M given data on H. And we also assume that we have two types of data, low fidelity data and high fidelity data. We don't know the exact value for alpha and M, but we know the range for alpha and M in a certain area. For example, in this case, this is the exact value for alpha and M. We don't know the exact value. But we can know the range for alpha and M. So we can just pick a value in the range for alpha and M, which is just here. And once we have the values for the initial gas, once we have the initial gas for alpha and M, we can solve this equation to generate a low fidelity data on H. And then we assume that we have two measurements for the pressure, high fidelity measurements for the pressure as high fidelity data. So in this case, if we only use these two high fidelity measurements as the data, as the training data to solve this inverse problem, this is the prediction for H for pressure, and this is the prediction for the permeability. The relative to error for the permeability is about 30% for single fidelity modeling. And if we use the low fidelity data and the high fidelity data here, and use the multi-fidelity pins to solve this inverse problem, this is a prediction for the pressure field, and this is a prediction for the permeability field, which is much more accurate, than single fidelity modeling with the same number of the high fidelity data. And we also have another example for PDE, which I will not show here. If you are interested in this case, you can try to refer to this paper. And recently, we also use this method to assimilate low fidelity data from some numerical simulation and the high fidelity data from sensor measurements to reconstruct the vortex-induced vibration from a marine riser to provide a guidance for the design of the riser. So in this case, we have lots of data from numerical simulation, and also accurate, and we also have some very few accurate measurements from the sensors on the riser, but we only have a very few of them. So we can use this method to assimilate the simulation data and also the experiment data or the sensor measurements to reconstruct the vibration of a marine riser to enhance the predicted accuracy. And then I'll introduce two uncertainty quantification methods in pins and also neural operators. So first of all, why we need why we need to develop Bayesian pins. As I mentioned, pins are efficient tool to solve inverse PDE problems. And here I have a very simple 1D inverse diffusion reaction system. And F is the right hand side, and the K is unknown constant in this equation. And we have measurements on both F and U. We would like to infer the unknown constant K here. The reference solution for K is 0.7. So basically, the measurements for F and U are noisy. So we can use the numerical solver to solve this equation to generate the training data, and then I add some noise in the training data for both the F and U. The blue points are the training data for F and U. And if we use pin to solve this equation, for this case, for the first case, I just add 1% error in the cleaning data, and the red dashed line is the prediction from pins for U and F. As we can see, we can get a very accurate prediction for both U and F. And this is a prediction for K, which also agrees well with the reference solution. In the second case, I try to increase the noise scale from 1% to 10%. And the red dashed line is a prediction from pins for U and F. As we can see, for the prediction for F, we get very significant overfitting results. And also since we cannot get a very accurate prediction for U and F, the prediction for K is also not very accurate. And so in this case, if we have very large noise in the training data, it's very easy to get overfitting. And the second issue for pins is, after training of pins, we can always get not just in pins, in deep neural networks. After training of neural networks, we can also get always get a prediction, but we don't know how good or how bad the prediction is. It means we don't have any uncertainty in predictions. So to address these two issues, the first one is the noise in the data will result in overfitting, and the second one is the uncertainty in predictions. We propose the following framework, which we call Bayesian pins. So this is a schematic of the Bayesian pins or B pins. We use a Bayesian neural network to place the fully connected neural network in pins. And in the Bayesian neural network, each weight and bias is a distribution instead of a point estimate in pins. For example, we can specify a normal distribution to each weight and bias in a Bayesian neural network. If we sample a weight if we get a sample for each weight and bias, we'll get a collection or a distribution over functions for U, which we'll call prior here. And if we have some data, we try to find all the functions in the prior space, which can fit data well. And those functions we call it posteriori. So if we write it in a mathematical way, which is the best rule. So we have a prior distribution for the weights and bias, and we have the likelihood for the data. And this is the marginal likelihood, and this is the posteriori. So if we can estimate, if we can get a posteriori, we can then get a posteriori for functions U here. And in this model, we treat the data as the likelihood part as a distribution. So all data can be noisy. So in this model, we can handle the noise data very easily. And if we would like to solve a PDE problem, we can also use the automatic differentiation to encode the PDE in this model. For example, here F is the right-hand side and B is a boundary condition or initial condition. If we have observations on U, B, and F, the likelihood will be the joint distribution for all the data here. So this is the first example is a function approximation case. We assume that we have 32 noise training data, and I use a Gaussian noise with 10% error, with a standard deviation 0.1 to contaminate the clean data to use it as a synthetic noise training data. The bullet points here are the noise training data, and the first one is the reference solution. The red dashed line is the predicted mean, and the field zones are the predicted uncertainty. And this is the reference solution. As for the posterior estimation, we can use different methods. For example, we can use Hamiltonian Monte Carlo or mean field variation inference. And or dropout is also kind of mean field variation inference. So we present the results with a different posterior estimate technique. So if we look at the comparison between the reference solution and the BN with HMC, you can see for regions we don't have training data, the uncertainty is very large. And if we go away from the data source, then predicted uncertainty will also increase. Also, for the computational error between the predicted mean, the red dashed line, and the reference solution, the computational error is bounded by the predicted uncertainty, which means if we don't have for cases that we don't have reference solution, we can use our predicted uncertainty to estimate the computational error. Also, so BN plus BN with HMC, it's the results from BN with HMC are very similar as the reference solution, but for the mean field variation inference and the dropout, the results are not so good. For example, here, if it goes away from the data source, uncertainty will not increase in the mean field variation inference, and also for dropout. The predicted uncertainty are not so good as in HMC. And as I mentioned, P is very easy to get over fitting results if the noise in the data in the training data are very large. So in this case, in the second case, I try to increase the noise scale from 0.1 to 0.5. And this is the reference solution, and this is the BN with HMC. As we can see in this case, we still didn't get overfitting result, overfitting. And the predicted mean, the combination errors between the predicted mean and the reference solution are also bounded by the two standard deviation, bounded by the predicted uncertainty here. So now we can also use BPIN to solve both the forward and inverse PDE problems. And the first test case is for the differential equation program, in which we have noise measurements on F, and we also have two noise measurements for U to serve as the boundary condition. And this is the reference solution for U. And in this case, we assume that the measurement error is a Gaussian distribution. It's Gaussian with 0 mean and 0.1 standard deviation. And this is a prediction using different methods, say HMC, IBiM plus mean field variation inference, and the dropout. And this is a predicted mean for U and the predicted uncertainty for U. And this is a prediction for F. So as we can see in this case, the computational errors between the predicted mean and the reference solution are also bounded by the predicted uncertainty. And this is an example of inverse differential equation programs. In this case, we have noise measurements on F, and we also have some noise measurements on U. Here, K is unknown, and we would like to infer the unknown parameter K here, given noise measurements on U and F. The blue points are the training data for U and F. And as we can see, this is a prediction for predicted mean red dashed line for U and F. In this case, both the prediction, the computation errors between the mean and the reference solution for U and F are bounded by the predicted uncertainty. And this is a prediction for the unknown parameter k here. We have tested two noise scale, 0.01 and 0.1. And this is a prediction mean for k in the first case, and this is a prediction for k in the second case. And if we look at the computational error between the prediction mean and the reference solution, we can see the prediction uncertainty has the same order as the noise scale. So in the first case, the prediction uncertainty has the same order as the noise scale here and also here. So this is also inverse PDE program, inverse differentiation program. We just try to say if we have less measurements on U, can we still get an accurate estimate for U and also the unknown parameter k here. So in this case, I reduced the number of the measurements for U from 8 to 4. And the red dashed line is the prediction mean for U, and the failure zones are the prediction uncertainty. As we can see, on the right half, even we don't have any measurements on U because we have encoded PDE in IBiM, so we can still get a very accurate estimate for U. And the computational error between the predicted mean and the reference solution is bounded by the predicted uncertainty. And also for U, this is a predicted mean for k. This is a predicted mean for k, and this is a predicted uncertainty. So as we can see, the computation error between the predicted mean and the reference solution is also bounded by the predicted uncertainty. Recently, we have collaboration with a professor from Stanford. And in this case, for this problem, we try to use BPIN to learn a dynamic model to describe the new cases, the dynamics of the new cases from data, and then we try to use the learning model to predict the new cases in the future. So in this case, we use the first 200 days data from the first 200 days to learn the model, and then we try to predict the new cases in the remaining, say, half a year. And the green dashed line is the predicted mean from BPIN and the failure zones and predicted uncertainty. And the orange line is the reference solution. And so in this case, we can also see the computation error between the predicted mean and the reference solution is bounded by the predicted uncertainty. So in the first part, we have multiple PIN, but we don't have any uncertainty quantification in our predictions. In the second part, we have uncertainty in our predictions. We only use single fidelity data. So we develop a new model to handle the problems with the multi-fidelity data, but also with the uncertainty in our predictions. This is a schematic of our proposed model, which is a multi-fidelity BNN. So in the first part, we also use a neural network to fit low fidelity data. And in the second part, we use the BNN to learn the correlation between the low fidelity and high fidelity data. Since we use BNN to learn the correlation, so we can quantify the uncertainty in the prediction of the high fidelity function. If we would like to solve inverse PDE problems, we can also use the automatic differentiation to encode the PDE in this neural network. So in this framework, we can handle noisy multi-fidelity data, and also we can provide uncertainty quantification on predictions. And now we would like to predict the surface temperature in the typical bay. So for this case, we have two types of data: the low fidelity data from sunlight, which covers the whole area, but the resolution is very low. And we also have another type of data, which are from the in-situ station, which are from the stations. They're very accurate, but we only have 40 measurements for high fidelity data. So in the training, we try to use the multi-fidelity BNN to assimilate the low fidelity data as well as the high fidelity data. In the training, we use 12 of the high fidelity data in the training, and about 2 as the validation data. So this is the prediction from the multi-fidelity BNN, the predicted mean and the predicted uncertainty. And this is the prediction from single fidelity modeling. By single fidelity modeling, I mean we just use the high fidelity data in the training. And this is a prediction for predicted mean and uncertainty for the temperatures at the 2 test locations. As we can see, the computational errors between the predicted mean and the reference notion are also bounded by our predicted uncertainty. So basically, for the CSF temperature prediction, it's actually a regression problem. We can also use this framework to solve inverse differential equation problems with multi-fidelity data. For example, here we have some measurements on F and U, and K is unknown constant here. We would like to infer K based on the multi-fidelity data on U here, and this is the low fidelity data, and we assume that this is the low fidelity data, and we assume that in this case we have 3 random high fidelity noise measurements for U and 10 random high fidelity noise measurements for F. So this is a prediction for from multi-fidelity BP. So we only have 3 high fidelity measurements for U and 10 high fidelity measurements for F. So as we can see, in regions that we don't have training data, the predicted uncertainty is very large. So if we have one more sensor for U and F, the question is at which location? So the question is, what should we add the new sensor for both U and F? And here we try to provide some guidance based on our predicted uncertainty. So we can add a new sensors at the locations that we have the largest uncertainty. But for example, here for U, we can add a new sensor here, and for F, we can add a new sensor at the location where we have the largest uncertainty. And this is the prediction after adding the new measurements for U and F. The blue cross here is the new measurements for U and F. As we can see, the predicted uncertainty, the predicted mean agrees better, and the predicted mean becomes more accurate, which is also reflected by the predicted uncertainty. So as we can see, the predicted uncertainty in this case is much smaller than in this case. So try to add more. Try to add more measurements. Try to add more based on our predicted uncertainty. So in this case, we try to reduce the predicted uncertainty by adding more and more measurements based on our predicted uncertainty. This method is called active learning. So we can add one more point with the location where we have the largest uncertainty. And this is animation unlike active learning case. For the active learning case, we can try to add more and more sensors to we can try to add more and more sensors based on our predicted uncertainty. And the result, as we can see, the results will be more and more accurate, which is also reflected by the predicted uncertainty. The predicted uncertainty will become smaller and smaller as we add more and more sensors. And this is a prediction for K. As we add more and more sensors, the prediction for K will be closer and closer to the reference solution here. thereby is prediction uncertainty for P. So for the last part, it's also a new uncertainty quantification framework. Based on it's a new framework, a new uncertainty quantification method based on GAINs. So for now, if we would like to quantify uncertainty in solving PDE problems, we mainly have two methods: the Gaussian process regression and then the BPIN we proposed before. In GP, we cannot use GP to solve nonlinear PDE problems, and the GP cannot also handle big data problems. In BPIN, we can handle any we can solve both linear and nonlinear PDE problems, but the prior is for in BNN. The prior is for the hyperparameters. For example, in the BPIN paper, we mainly use neural network with 2 hidden layers and with 50 neurons per layer. In the parameter space, it's more than 2,000 dimensions, which means we have to perform the posterior estimation in a very high dimension in a very high dimensional space. So it's very expensive, and it's also not very. It's also very difficult to get a very accurate estimation of the posterior. And second issue for BPIN is we set a prior for the hyperparameters when the weights and the biases in the neural network, but actually we care more about the prior in the functional space because we care about the solution to a PDE. But in a BNN, we can only set a prior for the hyperparameters for the weight and the biases. We don't know what the prior is like in the functional space. Certainly, researcher proposed to use generative adversarial neural networks to learn distribution over functions or stochastic processes. This is a schematic of the generative adversarial networks, which we call GAINs. It has a generator and a discriminator. The generator takes X locations or the coordinates, and also the samples from very simple distributions. For example, uniform distribution or Gaussian distribution. And then map it to a sample of a stochastic process. The discriminator is used to, and this is the sample from two samples from data. The training data is from a stochastic process or distribution over functions. And this is a training data for this is a loss function for training the generator and the discriminator. So after the training of the neural network, we can use the generator to approximate the distribution of the distribution over functions from the true data. And after the training of the neural network, excuse me for a moment. Sorry for interruption. So after the training of GAINs, we will have a stochastic process represented by a neural network. And if we have, if we would like to solve a PDE differential equation problem, we can also encode the PDE here using the same idea in pins. So since we have after the training of GAINs, since we apply our PI GAINs, since we have a stochastic process, we can use it as a prior in functional space. So basically, what we would like to do is to use the generator of GAINs to map a sample, to map a sample of simple distribution at the input space to a sample of samples in a stochastic process. So this is a framework we propose to quantify uncertainty in function approximation forward and inverse PDE programs, and also certainly propose the neural operators. So if we have a specified function distribution or simulation experiment data in the past, we will call it historical data. Then we can try to train a GAN or PyGAN if we have if we would like to, if the target program is a PDE program, to learn the distribution over functions or a stochastic process, and then we can use the stochastic process as the prior. If we have some new data on these functions, we can then perform the Bayes rule or Bayesian inference in the latent space or the input space. Once we get a posterior in the input space, we can then feed it to the generator to get a posterior samples in a functional space. For the posterior estimation, we can also use the Hamiltonian Monte or normalizing flows. So because the neural network is very expressive, so the number of the dimensions of the input space can be quite low. For example, we can use 20 dimension to 100 dimension Gaussian noise to fit most of the stochastic processes.
Dr. Meng, I need to ask you to go to the conclusion to allow some question time, please. Thank you.
Okay, sure.
Thanks.
Yeah, I'll just show some examples. So we can use this method to solve a fault to quantify uncertainty in pins, and also neural operator. Just show one example. For example, in this case, we have it's a Gaussian equation for the flow in porous media. H is the pressure and H is K is the permeability field. And to take a different permeability field into consideration, we use a model here to we use a truncated KL expansion for a Gaussian process to represent the different soil. So in parameter space, this is a 100 dimension program, and we can also use this method to quantify uncertainty in this program. For example, after we learn the functional prior for the permeability field and also pressure field, if we have some new measurements for K and H, we can then use our method to quantify uncertainty based on learned functional prior and also the given data. So that's the prediction for K and that's the prediction for H. As we can see, the computational error between the predicted mean and the reference solution are also bounded by our predicted uncertainty here. And so I think I don't have more time to talk about our open source library for uncertainty quantifications and information learning. So it's just released 2 months ago, and we can use this package to quantify uncertainty in pins and also neural operator and also for function approximation cases. If you are interested in this package, you can try to use this. You can refer to the GitHub link here. Okay, I think I will stop here to take any questions. Thank you, our collaborators.
Thank you very much, Dr. Meng. So we have some time for questions. As said, you can turn on your microphone, ask your question, or just write in the chat. So any question? Oh, okay, I may start with one. So meanwhile, we may have additional questions. It seems that based on your examples, yeah, you have tested your methods on, say, nonlinear functions and nonlinear PDEs. but they kind of all look to me. Yeah, there are some real world applications, but most of them are kind of periodic. So I was wondering if you tried these approaches to some, say, intermittent say, solutions or something similar.
Do you mean some more difficult PDEs or?
Yeah, I mean, in general, it seems that the solutions look like they are for sure nonlinear, but they are very periodic, or say they have they have a periodic nature somehow. So I was wondering how this works for some kind of intermittent solutions, which are.
Oh, actually, we just generate the training data based on this function. It actually doesn't matter. We also have some examples in which it's not a periodic solution. So we just randomly select this function to generate our training data, but it does have to be. So in our paper, if you try to look at read our paper, look at our paper, we have some more examples, and then the solutions will be more general.
Okay. Yeah, I think we have one question from the audience.
A nice talk. I think my question is about slide 20.
Slide 20. Okay. This one?
Yeah. No, the slide that, well, could you present that? Because it was animated, right? The one I'm thinking of is animated. It's what I would call an animated graph. And you can see the system approaching. It was quite spectacular, and it was early on in your talk. You know what I mean? There are curves. Yeah.
Here?
Try 12. Nope, try slide 12.
12, okay.
Nope. Maybe. Nope. Are we not going to be able to find this? It's a spectacular graph that you play, but this is not moving. There's nothing moving on that slide.
It's moving. Okay. Is that deep learning case? Yeah.
That's what I mean by animated graph. I don't really have a. Now, this is not the one I was thinking of. It came before this one. There's nothing spectacular about that. Go to it came before. Oh, try that one. Play that one.
Oh, this is not an animation. Just
it's got to be animated. It's got to be animated, and the lower right graph is the relevant one. Are you going to be able to find your way to it? Am I the only one that noticed this? It's got to be animated. That's not it. No, early on in the talk. Okay, go to the presenter mode, slide up, and let me see if I can identify it. It's got to be
okay.
Yeah, that whoa.
It's slide 2 or 3. Yeah.
This one.
There you go. That's right. Yeah, that's
okay.
Right.
Okay.
So first of all, what do you call a slide like that? An animated graph?
Do
you have?
It's just an animation. Anyway.
Yeah. Well, it's a graph and it's animated, so I'm giving it a name. I'm calling it an animated graph. Now, when you publish on this subject, do you publish the animated graphs?
No, this is not from my paper. It's from this paper. So in this paper, when the author published their paper, they have some animations for.
I see. So they are publishing animated graphs. Yeah.
Yeah.
The answer to my question is these are being published. I don't think, I could be wrong, but I don't think we've ever published an animated graph in physics of fluids. So I guess what I'm saying is not just to you, but to the whole audience here. Wow, this is really cool. It's not your work, but I'm glad you taught it to me. I've never seen it before. So to me, this is the highlight of the presentation today. And I think this is the future in comparing, you see? Oh my God, that's really pretty. It teaches us a lot about the system without words, you know?
So I did this experiment to generate animation. This is not from this paper, but they found the learning mode of the neural network in this paper from low frequency to high frequency. This is a learning mode of the deep neural networks. I generated the animation and also set up this case by myself.
Yeah. Anyways, thank you for this presentation. I enjoyed the whole presentation. This really stuck in my mind initially, and it got my creative juices flowing here. But I think those in the audience that are creating animated graphs should publish them with their papers, as this author did. And remember, anytime you're publishing animation, and I've said this before in this seminar series, include it as integral multimedia files rather than supplementary material, because integral multimedia is archival and supplementary material is not. So if you want this to be around 400 years from now for scientists to play video, you have to incorporate it as integral multimedia. Yeah, but I just don't think we're seeing enough animated graphs, I think, in general, in publications. These really communicate well. I think I've taken up too much time with my question there, Giovanni, but
yeah,
thank you,
no problem.
Mr.
Actually,
Chairman.
I agree with your free beginning. I was thinking for sure about supplementary material things, but yeah, perhaps in the future, this could be one way of communicating science for sure. Thank you for the feedback. Yeah, thanks a lot. I don't see any other questions, so I can thank again Dr. Meng for this very amazing presentation, and thank you all for attending this session. Of course, I would like to invite you to the next one on the IBiM seminar. So thank you all for attending, and see you soon. Have a nice rest of your day.
Thank you, Giovanni.
Thank you.
See you
Bye.
next week.
Cheers.